If you,
Oh, now it's recording. Okay, great. Thanks for letting me know. So today I'm going to introduce the coronary boundary condition, and this is basically a description and repetition of what's written in the SimVascular tutorial. So all the information, I would say most of the information is already on the SynVascular website, so you can revisit it there anytime. So, so I'll first introduce the three-dimensional aortal coronary artery model and how it looks like, and I will show them on SimVascular, and then I'll go over how to assign boundary conditions at the coronary arteries step by step, because there are multiple steps to really get the parameters in the uh, electric circuit to input to our model. So I'll go step by step. The first, as you guys have, you know, been through the tutorials, SimVascular can basically read medical image data and then generate PET line and segmentations on that. And then you can load those segmentations to build a three-dimensional anatomic model. And then you can mesh it and then perform some simulations to get some hemodynamic data. We frequently use this 3D and 0D coupling approach. So we have three-dimensional model, and we couple the three-dimensional model with the 0D circuit at the inlet and outlet of the coronary. So this is an example that we use for our study. And this is more like a closed loop model. But what we're gonna talk about is our open loop coronary artery model. So usually we couple this uh, three-dimensional model with the heart model, which is in 0D model. But you can choose other boundary conditions rather than the closed loop model. So when you visit the SimVascular website, there's a clinical case studies tab, and there's the coronary normal tab. So you can download the whole SimVascular project from the website. And this is the aortal coronary model that you can get from the website. So the aortal coronary model consists of like basically two parts. The one is a part of the aorta that comes out of the heart, and the second part is the coronary arteries, which consists of actually left and right coronaries, and the coronary arteries have like multiple branches. The aorta has like large diameter, probably the largest diameter of the blood vessels in the body, and coronary artery has like small diameters. So there's sort of like a scale separation between these two. So basically, this is the structure of the aortal coronary artery model. So how do we assign boundary conditions on the aortal coronary model? Um, Basically, at the inlet of the aorta, you can attach that to the 0D heart model as I showed before, or you can directly prescribe the flow condition at the aorta. So you can basically assign time history of aortic flow waveform. Uh, and it usually goes like mean flow rates of around like 100 milligram per second. And at the outlet of the aorta, you can attach like RCR boundary condition that you can incorporate the resistance and also the capacitance effect of the downstream blood vessels. At the outlet of the coronaries, we'll need a special type of boundary condition than a simple resistance or RCR boundary condition, because as I showed before, coronary artery has special physiology. So we need to prescribe a special type of boundary condition to reproduce a correct physiology inside the coronary artery. So what's the physiology in the coronary artery? So this is the typical pressure waveform in a heart cycle. It goes up at systole, and it goes down to the diastole phase. And when pressure goes up, as heart muscle contracts, the flow in the coronary artery actually it's actually low. Most arteries have similar waveform as like the pressure waveform, because the pressure waveform is the driving force to the flows in the blood vessels. But in coronary arteries, since the heart muscle contracts, flow is now impeded. And as the heart muscle relaxes, and the flows in the coronary artery actually has a peak. So almost like the starting phase of the diastole, the flow in the coronary artery has a peak. So in order to model this physiology in our like boundary conditions, basically, we need like multiple circuit elements, including some resistance values and capacitance. And here's the special value, which is the pressure inside the myocardium. So coronary boundary condition is basically looks like this circuit, and we need to prescribe each circuit element's values to reproduce the correct physiology of the coronary artery. I'm referring to some of the papers, and these papers have like derived this electric circuit, and also they sort of like give some estimates of how do we distribute these like values inside the coronary arteries. So if you guys have need further readings, please refer to those papers. So how to determine each circuit element values? So we'll go over some of the physiologic rules that governs the hemodynamics inside the coronary arteries, and also in general how the flows in the small branches of the artery is estimated. So first, we should determine how much is the resistance of the coronary artery circuit. So basically, coronary artery circuit consists of RC/RCR circuit plus this pressure value. So we need to determine what's the resistance of the coronary arteries. The first rule I would like to introduce, that is the 4% rule. So we assume 4% of the total systemic flow goes to the coronary arteries. So some of the coronary artery flows, both in left and right coronaries, is only the 4% of the total systemic flow. There is clinical evidence measured by some of like magnetic resonance imaging that this like 4% is sort of correct. The 4% is not the golden rule, so it does not affect to everybody. There might be some patient specificity and inter-patient variabilities, intra-patient variabilities, but this 4% is a reasonable assumption that we can apply to our um, modeling study. So basically, if we know how much is the systemic flow rate, and then we can multiply by 0.04 to calculate the flow in the coronary arteries. And we can flip this to resistance, basically. And if you have like higher resistance, you would expect like low flow in that vessel. So translation of this equation in resistance perspective is like the total coronary artery resistance is 25 times higher than the systemic flow resistance. So how to calculate the systemic resistance is like you can basically take the mean pressure and systemic flow, which is like cardiac output. So this is just an example of how to estimate the systemic total resistance. So most people have cardiac output like 5 liter per minute. And then you can use these values to estimate the total resistance, and then you can multiply by 25. Usually, left coronaries have more number of vessels and larger flows than the right coronaries. And there's a flow split between these two. So within the 4%, you can split the total coronary artery flows with 70 to 30% ratio. So you can then calculate how much is the total resistance of the left coronary branches and total resistance of the right coronary branches. So once we have the total resistance of like each right and left coronaries, then we distribute the total resistance to each branch. So this is a left coronary branches. So this is the left anterior descending artery, and this is left circumflex artery in coronary arteries. And each outlet of the branch, we would like to assign correct boundary conditions that can correctly capture the flow distribution inside the coronary arteries. So we use the Murray's law to distribute the total resistance to the branch. So we know the total resistance at the left coronary, and we want to know how to distribute it. So we are using this rule that the flow rates in a branch, it's actually proportional to the diameter to some exponent, which is 3 for microvasculature. This is very famous Murray's law. This is a morphometric law that how each branch has flows. So the exponent is 3 for microvasculature. And following the Murray's law, flow is proportional to the d to third power. And if you flip it, the resistance of each branch is proportional to diameter to inverse of diameter to the third power. And the diameter is approximately square of the area. if we assume a circular shape of the vessel. So the Murray's law is very well accepted and validated against like histologic data. Um, but it's well fitted for the microvasculature. That means like it scales around sub-micron scale. But for coronary arteries, it's actually bigger than that. So we have some modified exponent, which is 2.6. So when we calculate the resistance at each outlet of the coronaries, we now use the 2.6 rule instead of 3 exponent. So when you have the total coronary resistance, you can distribute each coronary artery resistance by multiplying by this factor. And then at each coronary artery outlet, we want to distribute the total resistance to 3 circuit elements resistances. So there's like proximal resistance. I like denote it as like RA, and there's like second resistance next to the proximal, and there's like third part of the resistance. So the sum of these 3 factors is actually 1. So we distribute the total resistance to 3, and there's ratio between these 3 elements, which is 0.32, 0.52, and 0.16. The ratio is driven by some animal experiment data and also previous studies. So you can basically borrow these values for the coronary artery modeling. And we also need to prescribe the capacitance in the circuits. There are 2 capacitance. One is compliance of the proximal coronary artery, and another is the capacitance of the myocardium. And basically, we distribute the total capacitance to each branch as like the resistance. So for basically the golden rule for assigning capacitance values is basically you want to match the patient-specific clinical data. So you basically tune this parameter to match the pressure waveform, the magnitude of the pressure waveform that you observe from a patient. But in order to tune it, you need to start from a initial value, and a good starting point is like these values. So you can take a reference and then start from that, and then perform some preliminary or prototyping simulations and tune this parameter afterwards, basically. And how do we distribute this capacitance to each branch? We assume that the capacitance of the vessel is proportional to the area. Basically, the distensibility of the blood vessel wall, we assume that's actually proportional to the area, or square of the diameter or something. So each coronary outlets, as like resistance, you basically distribute the total coronary capacitance with this ratio. The difference between the resistance and the capacitance is like the exponent here, basically. And then basically you can assign each circuit element each circuit like capacitance values. There are two by multiplying these two factors, and also these two factors are based on some animal study. The last thing you want to prescribe is the intramyocardial pressure, and this is actually the key part of the coronary artery boundary condition. And without the intramyocardial pressure, this is just like a simple RC-RCR circuit, and you wouldn't expect any out of phase behavior in the resulting simulation data. But as we put this intramyocardial pressure circuit elements in here, and it acts like a time variable resistance at the downstream of the coronary artery. So what we prescribe is the some pressure waveform, which is sort of similar to the aortic waveform. You have the peak waveform at the systolic phase. So what it means is like you have like high pressure at here, and it impedes the flows at the coronary arteries, basically. A previous study examined that this intramyocardial pressure is proportional to the left ventricular pressure. Basically, these two pressures, like intramyocardial pressure and the left ventricular pressure, they are different. But we actually don't know, or it is very hard to measure the intramyocardial pressure. So we are basically approximating the intramyocardial pressure with the left ventricular pressure. In SimVascular, this intramyocardial pressure value is provided. So as a sample, basically, and then you can multiply a scale factor for your own specific coronary artery modeling. So you can multiply this factor by like 1.5 or 0.5, and then after you run the simulation, then you need to check like this multiplication factor is well prescribed or not. So this is the resulting pressure waveform at the coronary artery. This is the flow waveform at the left coronary artery, and this is the right flow waveform at the right coronary artery. After we prescribe all these boundary conditions that I explained before, so you can see the nice out of phase behavior in coronary arteries, so it can now reproduce well the physiology of the coronary artery in the model. Basically, what you need is like, if you know what's the cardiac output at and the mean pressure at the aorta, and then you can basically derive what's the resistance of the coronary arteries, basically, and then you can distribute the capacitance of the total coronary arteries to each branch. And in order to distribute the resistance of the coronary artery, you need to calculate the outlet areas of each coronary artery branch. And then you will need the time history of intramyocardial pressure or the left ventricular pressure. In SynVascular example project, this is already provided. And these are our lab references about the coronary artery modeling. So, and these are basically how these boundary conditions are used in patient-specific models for specific disease. That includes coronary artery bypass graft surgery, and also Kawasaki patients and some uncertain quantification study. So I will now go to SimVascular program. So I sort of like loaded the projects that you can download from SimVascular website. So this is your image data, and there's a coronary artery model. So this is your heart, and this is your aorta, and there are coronary arteries. And it's pretty simple. So when you go to simulation, and then you will need some basic parameters. I think Casey will go over each of them. And basically, when you assign these boundary conditions, you can just like click coronary, and there are RC, RC, R values from proximal to distal. So you put all these numbers that's calculated by the morphometric law, and then you provide the intramyocardial pressure, tiny sort of it, and it's you can basically load from that from your SynVascular um, example, and this is the scale factor that you multiply to the intramyocardial pressure curve. So in the left coronaries, it's 1.5, and if you go to some right coronaries, it's 0.5. And this is the intramyocardial pressure period, and that should be consistent with your um, heart cycle, basically. Okay. With that, I would like to conclude my tutorial. So I'll take any questions.